Uh, I'm very pleased to be here today to talk to you all about my repair the damaged brain. I'm particularly excited about this field because as a hopeful neurologist myself, I figure this offers one of the great ways we may be able to offer hope for our patients who live these devastating yet untreatable diseases of the brain. Made my way to Ithaca, New York from Wilmington, Delaware. I'm going to be a senior in high school at Concord High School this year. So here's the problem. You can see here, picture somebody's brain with Alzheimer's next to a healthy brain. And what's obvious in the Alzheimer's brain, ring red, there's obvious atrophy, scarring. And I could show you equivalent pictures from other diseases, multiple sclerosis, motor neuron disease, Huntington's disease, and they would all tell a similar story. And collectively, these brain disorders represent one of the major public health threats of our time. And the numbers are really rather staggering. At any one time, there are 35 million people today living with one of these brain diseases, and the annual cost globally is $700 billion. I mean, just think about that. That's greater than 1% of the global GDP, and it gets worse because all these numbers are rising because these are, by and large, age-related diseases, and we're living longer. So the question we really need to ask ourselves is why, given the devastating impact of these diseases to the individual, never mind the scale of the societal problem, why are there no effective treatments? Now, in order to consider this, I first need to give you a crash course in how the brain works. So, in other words, I need to tell you everything taught at medical school. But believe me, this isn't going to take very long. So, the brain is terribly simple. It's made up of 4 cells. 2 of them are shown here. There's a myelinating cell, or the insulating cell, and they're called alkadendrocytes. And when these 4 cells work together in health and harmony, they create an extraordinary center of electronical activity. And this electronical activity underpins our ability to think, to emote, to remember, to learn, to feel, and so on. But equally, or individually, these 4 cells can go rogue or die. And when that happens, you get damage. You get damaged wiring. And that becomes evident with slower conduction. But ultimately, this disease will manifest disease clearly. And if the starting dying nerve cell is a motor nerve, for example, you'll get motor neuron disease. So I know what you're thinking. My God, this kid came up and said all he was going to talk about is hope. And all he's done is rather give a bleak and depressing tale. I've told you the diseases are terrible, they're devastating, numbers are rising, the costs are ridiculous, and worst of all, we have no effective treatment. Where's the hope? Well, you know what? I think there is hope. And there's hope in this next section of the brain with somebody with MS, because what it illustrates is amazingly, the brain can repair itself. It just doesn't do it well enough. And so again, there are 2 things I want to show you. First of all, as a patient, I worked at NAMI, and what it shows is that the blue masses were once blue, and then they became white, which means the disease has now been manifested and damaged and repaired. Just be clear, this is not because of doctors. This is in spite of doctors, not because of doctors. This is a spontaneous repair, and it's amazing. And it occurs because there are stem cells in our brain which enable new myelin, new insulating cells, to be laid down over those damaged nerves. And this observation is important for 2 reasons. The first is it challenges one of the orthodox taught at medical school, admittedly last century, which is that the brain doesn't repair itself unlike the bone or liver. But actually it does. It just doesn't do it well enough. And the second thing is this, it gives us a new direction for new travels of therapy. I mean, you don't need to be a rocket scientist to know what to do here. You simply need to find ways of promoting the indigenous, spontaneous repair that occurs anyways. So the question is, why, if we've known this for some time as we have, why do we not have those treatments? And this in part reflects the complexity of drug development. Now, drug development you might think is a rather risky bet against the odds, and the odds are roughly this. There are 10,000 to 1 against, because you need to screen about 10,000 compounds to find one potential winner. And then you need to spend about 15 years and over $1 billion. And even then you might not have a winner. So the question for us is, can you change the rule of the game? Can you shorten the odds? And in order to do that, you need to think, where's the bottleneck in drug discovery? One of the bottlenecks in early drug discovery is that all the screenings occur in animal models, but we know the proper study of mankind is man, to borrow from Alexander Pope. So the question is, can we study diseases using human materials? And of course we can. Absolutely we can. We can use stem cells, and specifically we use human stem cells. And these human stem cells are extraordinary but simple cells. They can do two things. They can make more of themselves or create new. But they can also become specialized to make bone, liver, or crucial nerve cells, maybe in the motor nerve cell or the myelin cell. And the challenge has long been, can we harness the power, the undoubted power of these stem cells to realize their promise for regenerative neurology? And I think we can. The reason we can is because of several major discoveries in the last 10 to 20 years. One of them was in Edinburgh, and it must have been the only celebrity sheep, Dolly. So Dolly was made in Edinburgh, and Dolly is an example of the first cloning of a mammal from an adult cell. But I think more significant breakthrough, as the purpose of our discussion today, was made in 2006 by a Japanese scientist called Yamanaka. And what Yamanaka did, a fantastic form of scientific cookery, was he showed us that just four ingredients, could effectively convert any adult cell into a master stem cell. And the significance of this is difficult to exaggerate, because what it means is from anybody in this room, but to particularly patients, can now generate a bespoke, personalized tissue repair kit. Take a skin cell, make it a master pluripotent cell, so you can make those cells relevant to their diseases, both to study, potentially to treat. Now, the idea of that in medical school, this is a recurring theme, isn't it? Me in medical school, would have been ridiculous, but it's absolutely reality today. And I see the cornerstone in regeneration, repair, and hope. So, to return to the original problem, what is the opportunity of these stem cells, or this disruptive technology, for repairing the damaged brain, which we call regenerative neurology? I think there's two ways you can think about this. It's a fantastic 21st century drug discovery tool, and is a form of new therapy. Drug discovery in a dish is how people often talk about it. It's very simple. You get a patient with disease, let's say motor neuron disease, take a skin sample, you do a pluripotent reprogramming, as I've told you before, and you generate live motor nerve cells. That's straightforward because the pluripotent can do that. But crucially, you can compare these behaviors to their equivalent but healthy counterparts, ideally for unaffected relative. That's the way of the matching genetic variation. Now I want to talk about how we might use these stem cells directly to repair damage. And again, there are two ways to think about this that are not mutually exclusive. The first, and I think in the long run will give us the biggest dividend, but is not thought of that way just yet, is use those stem cells that are already in the brain. Everyone has stem cells in the brain, even the diseased brain. And surely the smart way forward will be to find ways to promote and activate those stem cells in the brain already to react and respond appropriately to damage to repair it. That will be the future. There will be drugs that do that. But the other way is to effectively parachute in cells, transplant them in to replace dying or lost cells, even in the brain. So I just want to end with the theme I began on, which was regeneration and hope. Up at Cornell this week, I've been fortunate enough to meet a patient named John. And what John will show is not only the shocking pace of the disease, but it can leave a young, fit, adult man wheelchair-rented and respirator-dependent in just 16 months. Let's face it, John's can be anybody's uncle, brother, or cousin. So I don't know if you caught all of that, but he said, hopefully, with research, they can come up with a cure for his disease, motor neurons, also known as Lou Gehrig's. And I mean, that speaks volumes. But I'd like to close by, first of all, thanking John and Cornell for having me here. But I'd also like to add to John and others that my own view is I am hopeful for the future. I do believe that the disruptive technologies like stem cells that I've tried to explain to you really do offer hope. And I do think that the day we might be able to repair the damaged brain is sooner than we think. Thank you. Thank you. Thank you. Thank you.